Hello, everyone. I am Aaron Johnson, the Executive Director of the American Institute of Professional Geologists, and I would like to welcome you to our Lunch and Earn webinar for April. Before we get into the webinar and before I introduce our speaker, I'd like to maybe take care of a couple of little bookkeeping or housekeeping things. First, if you need a certificate for your CEUs, that certificate will be automatically sent to the email address that you used to register for this webinar. So if you don't receive that in the next couple of days, reach out to us and make sure that we did get that address correct. Mistakes do happen. We are human. If you need continuing education credits for New York State, you do have to take a quiz. That's a requirement for the New York State Education Department. That quiz will be placed, a link to that quiz will be placed into the chat late in the webinar. We'll place that in your chat. You'll click on that then. We'll try to keep that open for about an hour afterward. If something does happen and you're unable to immediately take that quiz, please reach out to us. We can keep it open longer, but we need to know that that request is going to be necessary, so please contact us. Today, I'm pleased to introduce Jason Thomason. Jason is the section head for hydrology and geophysics for the Illinois Geological Survey. He did a bachelor's degree at Bradley and a master's in hydro at Illinois State, and then went on to get a PhD at Iowa State University. Jason's been with the survey almost 2 decades, and today he's going to talk with us about how you can map an aquifer using some airborne geophysics. Jason, thank you for sharing your time and expertise with us today. The floor is yours.
Great. Thanks very much, Aaron. And thanks to AIPG for the opportunity. Yeah, I, again, have been with this organization for quite a while now and have been fortunate enough to get involved with a project with this evolving technology of airborne geophysics. We started to get involved with it back in 2013, trying to build momentum when the USGS was really starting to get involved as well. And we finally started to secure some funding and do some projects with this mapping technique. It's really changing the way we do things. So I'll give you an overview of kind of where we are with our program and some of the aspects of what we've been working on mapping an aquifer in East Central Illinois. And we'll see, this was working earlier. Here we go. This aquifer that we've been focusing on is something that's not unfamiliar to us in Illinois. This is called the Mahomet Aquifer, and in East Central Illinois, where everywhere you see in green here is where we have generally mapped where the aquifer is. We've been studying this aquifer for decades and decades. And we've gotten to the point where we have lots of monitoring, lots of modeling, and now we need to take another step into developing our science associated with this aquifer. It provides drinking water from anywhere from 500,000 to 1 million people, depending on who's counting, across all of East Central Illinois. And we'll get into it a little bit later, but in the eastern portion of this aquifer, it's confined. In the western portion, it's unconfined. So there are some complexities associated with it that we try to understand. Given withdrawals over time, it can be up to 220 million gallons of water a day. That's collectively with communities and industry and irrigation. Irrigation is a huge consumer of this aquifer system and aquifer resource. Recently, in recent years, there have been some legislative actions and that have grown the awareness of this aquifer resource in Central Illinois. In 2015, the US EPA designated it as Illinois' only sole source aquifer system that was charged largely by local advocates and local citizens who really promoted this designation. And then in 2017, we were helping with the Illinois EPA and other group and other scientific leaders to pass Illinois legislation to create a Mahomet Aquifer Task Force. And then from there, we've been able to then hold public workshops and really help the general public and our legislators learn about the aquifer and different ways we can improve our science of the aquifer. And then in 2022 and 2024, we've actually then got some funding to do some of this new airborne geophysics mapping. To just review some of the complexities I mentioned about this aquifer, this is from a publication from a few years ago, from 2017, where they were looking at the impact of the aquifer on the 2012 drought in the central United States. This is a map where you see in white here is all where we've mapped where the aquifer is. The red bands are the drawdown from pumping, from irrigation pumping, these red zones, irrigation pumping in that early to mid-summer of 2012. All these green dots over here are irrigation wells, again, over in the unconfined portion of this aquifer. So this is drawdown during the drought, but we have literally no drawdown down over here in the irrigation portion of the unconfined part of the aquifer. In the confined part of the aquifer, we have significant drawdown in other parts of different counties. So that's an added complexity to this whole system, is parts of it are confined, parts of it are unconfined. After that drought in the early to midsummer, Hurricane Isaac came through and dumped a bunch of water into the system. And so those irrigators in the confined portion turned their wells off, and we had rebound. The blue is an indication of rebound from drawdown. But then this town of Decatur, which is a mid-sized city, it has a well field in the aquifer, and they turn on that well field to then dump water into their surface reservoir, which is north of town. So they dump it into the stream, it comes down and refills their surface reservoir. So it has impacts as well when they decide that they want to turn on their emergency wells, to say. And as a result of that, as a result of the drought and that pumping from the town of Decatur that's out of the aquifer, there's sometimes conditions where this major watershed river, the Sangamon River, will actually dry up and have dry bed conditions. So a lot of what my colleagues who are water scientists and groundwater flow modelers are trying to understand the geologic framework and all the complexities that come with pumping, with irrigation, with precipitation, along with hurricane events. So my point is it's a complicated system that we're trying to learn better. And one of these ways is by using helicopters, for example. Our origins of kind of understanding this aquifer extend back to the 40s and 50s, at least with our scientific surveys, for example. So a gentleman named Horberg back in the 40s was discovering the Illinois portion of the Taze-Mahomet bedrock valley that extends all the way over to Ohio. This is certainly a bedrock valley that's host to many sand and gravel aquifer systems throughout these three states. Started to develop cross sections back in the 40s and 50s to develop the stratigraphic framework. In the 60s, we really started to map out the aquifer sediments in more regional studies. In the 90s, they started to really, these are colleagues of mine when I say they, but they started to really develop the stratigraphic framework, so we understand and try to put the sediments in a geologic framework. And this framework is ever evolving as we gain more information. Wilson and others in the 90s started doing some flow modeling of the system. And there were early flow models, I think as early as the 60s or so. But these are some of the more robust computer models, iterative models that were starting to be developed in the 90s. Even more robust modeling then by my colleague George Roadcap at the Illinois State Water Survey, and his colleagues started to do some more advanced predictive modeling with 50-year predictions that include population growth and usage growth and all that. Some fantastic modeling resources, all associated with the Mahomet Aquifer. And then some private work that was funded through the local water company, funded some of our geologists to really dig deeper into the stratigraphic framework to understand distribution and materials associated with the whole system. So some detailed cross-section work, detailed reporting of sediments in the framework of the Muhammad Aquifer. And then most recently after that, that's led us to really trying to understand a third dimension of the aquifer. We wanted to move beyond cross-sections, move beyond basic understanding. And as the technology developed in the mid 2010s, we jumped onto that technology and gained support and funding to really start to develop our vision of how we're going to move forward with the future of science with this Muhammad Aquifer thing. So we developed some publications and some vision, and gained some funding for doing some helicopter-based geophysics. Again, we can never do projects like this. Many of us, this is not an uncommon slide, but we can't do projects like this without collaborations from many people. We've had collaborations with local leaders, county leaders, city leaders. Excuse me. Support from state legislators who are really driving a lot of this. And we've even gotten funding and support from federal legislators. Our Illinois state senators, Richard Durbin and Tammy Duckworth, have been advocates for this technology and using this technology for mapping. And of course, with these projects, there's a whole army of folks within our organization who help with this, anything from the state geological survey to the state water survey to our administrative staff. We've collaborated with the USGS as well, who've also done a lot of this work. Students from many different universities, largely the University of Illinois and Illinois State, all the way down to collaboration with a local junior high school who let us drill a nice strategic test hole on their property. So it's been a great collaboration over the last couple of years with this project. So we've been able to get funding and focus our first efforts with airborne mapping in Champaign County. We are our group, our state survey in the University of Illinois is located in Champaign-Urbana. Champaign-Urbana is the largest user of the Muhammad Aquifer. We have well fields out to the northwest that supply all the water for Champaign-Urbana, and then Champaign-Urbana distributes actually, or the water company that that runs the well field supplies water to many different municipalities and small towns around. But many of these other towns are independently on their own wells and well fields. So what was our objective for airborne mapping? Well, we wanted to change the way we do this. We knew we couldn't just keep drilling and keep mapping with boreholes and water well records. We had to figure out another way, and we've used ground-based geophysics a lot, but this is just one way to step up the game. And pretty much the only way we can effectively move forward with Muhammad Aquifer science. Specifically, we've been studying this thing for 60 years. It's time to move to a new realm. We want to know exactly where it is now. We had a rough idea. We have a rough idea, and we want to know exactly what it's like. We want to know where it's gravelly, where it's sandy, where it has silt lenses, where all these things are, and fill in all the gaps from where we don't have data, which is the objective of airborne geophysics. And from those, we'll develop detailed maps, detailed tools that stakeholders can use. Usually they want maps. They want to know where they can put a new well, and where they can develop planning. And so we'll try to develop those types of tools, but then also integrate all these data into our colleagues' flow modeling efforts to basically, in my opinion, make one of the most robust decision-making programs probably in the country, hopefully. So how does this whole system work? If you're not familiar with it, it's there's a photograph of the system when we used it up in the Chicago area, where a helicopter basically tows the whole thing. There's a generator, actually a flying generator, gasoline powered generator that powers the whole system. This whole thing is a transmitter loop that emits electrical energy into the ground down to about 1,000 feet or so. And that energy comes back and the receiver records that energy. There is a magnetometer, an altimeter, an inclinometer, all being measured. And the pilot is measuring the altimeter and the inclinometer as he or she is flying to make sure they're as level as possible. Basically, as it gets off the ground, then that helicopter and the pilot have a navigation system that takes them back and forth and back and forth and back and forth. And this is how we've flown Champaign County, for example. We'll get into the details of this, but it's basically flying transects across the county. And we decided on what resolution of transects prior to flying. So the electromagnetic energy gets emitted into the subsurface. There are all these eddy currents that occur as a function of interacting with the subsurface. That's all the geophysics realm that I'm not all that familiar with. But in the end, we get these profiles of electrical data. It's just like a ground-based electrical resistivity profile, but it's airborne. And so we really start to see the details of geology. And then, of course, we can take all these profiles and compare to whatever other data we have. We have lots and lots of water wells, thousands of those, of course, with varying quality. We have our own test holes. We have, over the years, we probably have over 100 of our own geologic test holes or engineering borings that are down to bedrock. So we have very good control, reasonable control with our own geologic boreholes. And then we interpret that as geology. We'll see that again. So, given some of the errors in the data that we can identify from anthropogenic sources, we try to clean those up. But then in the end, we try to interpret these profiles. Other organizations have used this around the country for sure. I'm not as familiar with this, but the California Department of Water Resources clearly have identified this as a viable method for mapping aquifer resources. Of course, California is the top of the line as far as water security and trying to understand their water resources. So they've flown basically the whole San Joaquin Valley with this technique at quite a high resolution, it seems. So they're really taking the initiative to use airborne electromagnetics to map water resources. The USGS has also been a leader in this throughout the country. They've flown, this is just an example of a poster that they've flown out in Nebraska and in the Missouri River Valley. They've flown in Illinois as well. We've collaborated with them, flown through Illinois and Wisconsin and Mississippi Valley. So they've really been great collaborators and leaders in using this technology for specifically aquifer mapping and water resource mapping. We've also used this along the shores of Lake Michigan, not for aquifer mapping, but for sand distribution mapping. Quite a few years ago, this was our first project in Illinois, where we used airborne EM to map a timestamp in sand distribution along the coast of Lake Michigan, because there's so much infrastructure and so much erosion of the lake shore that people are trying to get a handle on erosion rates and causes of erosion and how that affected with lake levels, etc. So this is a fantastic first shot at using the technology in Illinois. So my colleague Kisa Mwakanyamale, who is a co-presenter with me here, has been leading our efforts in Illinois, and she led this Lake Michigan project as well. So back to the Mahomet Aquifer, we received some funding from the county themselves. Champaign County, our local county, has been local leaders in promoting and investing in Mahomet Aquifer research. It is the county's only water resource. So they are really invested in protecting it, understanding it, and they've been advocates for us and great collaborators with us in the science and the future science of this resource. So using HTEM, we like to try to think. We call it HTEM. Sorry, airborne technology. We try to communicate what are we going to see with these data if we collect it. Well, first thing, we will see that land surface topography, which is all in much of the upper Midwest and in Illinois for certain, is dominated by ice age history. So this is a map on the right of Champaign County where we have glacial moraines, clay-rich glacial moraines that are intersecting and crossing each other. We have interlobate moraines here and terminal moraines. Lots of course, every stream that we have is a function of ice age history and drainage off of these ice sheets. So we have major watersheds that are a function of ice age history, and then also the materials associated with this ice age history. So again, clay-rich moraines, sand and gravel outwash fans in front of these moraines, which are sometimes used for shallow water resources and domestic resources. These sand and gravel outwash fans. We also have these valley trains and modern streams that were also housing meltwater discharge off of these ice lobes. So we have a very strong glacial history in Illinois and a clear stratigraphic record. I say clear, but a generally robust stratigraphic record that we've been able to figure out over the years. But all of this complexity leads to fairly complex cross sections. This is one of the cross sections by my colleague Andy Stump, who worked back in 2015 to really try to piece out more details in the stratigraphic structure of the Mahomet Aquifer system. These brown sediments in this cross section, these brown units are classified as the Mahomet Aquifer, but we have all these pink units, which are glacial tills, clay-rich tills, carbonate-rich tills, along with sand and gravel lenses from younger glacial events, and then the youngest glacial events from the last ice age are these green clay-rich deposits, along with other outwash fans and modern river valleys situated on top of these clay-rich deposits. So it's a rather complicated stratigraphy, a complicated geology, but the Mahomet Aquifer sediments are some of the oldest sand and gravel sediments and glacial sediments, quaternary sediments in the area. So the complexity here is something we want to try to figure out a little bit more using these airborne methods. We'll also be able to really figure out bedrock topography much better. This is a more recent version of bedrock topography and interpretation based on well records, where we have these deeply incised bedrock valleys that are on the order of little over 100 meters deep, potentially, in their deepest parts, but with tributary valleys coming into these major bedrock valleys. This major bedrock valley is called the Mahomet Bedrock Valley. And at that, pre-glacial times, it was filling with sand and gravel deposits. It was active, free-flowing rivers as glaciers were approaching and dumping lots of sand and gravel into these valleys. And from our understanding over the years, this RoadCap 2011 interpretation of where the boundary of the Muhammad Aquifer was has been used for a long, long time. And this is an iterative boundary that's been developed over decades. And then Andy Stump, the one who developed those cross sections, came up with his own boundary based on his own interpretations, his own cross sections. So we really want to try to redefine this. We really want to define what we know as the aquifer boundary, which is not a very easy thing to do, even with airborne methods. But we really want to try to define where this is, largely for planning tools. So how do we do it? Well, with the airborne technology, we flew transects across the county, east-west, every 2,000 feet. We did every 650 meters. So overall, we had 79 transects, 2,200 linear miles, a little over 3,000, or yeah, a little over 3,000 kilometers, linear kilometers of transects. So it was very good resolution relative to the scale of a county, the best resolution we'll ever get with data. So we can start to figure out bedrock geology, bedrock topography, along with the infill of all the glacial materials. And this is the first shot kind of what we've been looking at with the HTEM data. This is a perspective view of vertical profiles. So these are all these flight line profiles that we display as vertical profiles of electrical data. And then we start to see different trends. We see that these red blobs in here are likely sand and gravel blobs. The green up here are these glacial moraines, the clay-rich moraines. The blue down here are clay-rich moraines along with shale bedrock. These very non-conductive or very conductive, electrically conductive materials, shales. Whereas sand and gravels and coarser materials are poorly conductive. So those are kind of the red colors. We use a red rainbow color ramp for these kind of representations. So at a first shot, we can start to see where these are old boundaries, the road cap boundary here of the southern boundary of the aquifer. This is Andy Stump's boundary. And we start to see how there are discrepancies between their boundaries based on water well records and our boundary based on HTEM data. So our boundary, I say our boundary, but it's just a new interpretation. We're trying to figure out, a different resolution, a higher resolution of where this southern boundary of where this aquifer is. And I think we're getting close to that. There are other ways to look at these data. These are just a few weeks old. These different ways we can slice and dice through the data. We've been trying to interpret profiles for quite a few months now, but we've been able to use these electrical data and do different types of inversions, three-dimensional inversions on the data with different softwares. I will mention too that just to go back for a second, we have these big gaps in the data. Sorry, I didn't mention this, but we do have little gaps here and here and here. These gaps are basically municipalities and towns. So these are a row of little small towns along a highway. This is Champaign-Urbana, and there are just too much electrical disturbances in those areas, and too much infrastructure, so that the helicopter, we can't fly over that. One, because of FAA reasons, and two, because it would be pointless. There's too much electrical disturbance. So those are the urban areas we have to stay away from, but we fly pretty much everywhere else. So anyway, with those different inversions, we can do 3D inversions and then take horizontal slices of the data and really start to see some of these details of not only the geometry of where the aquifer is, but the character of the materials themselves, where it's more red versus more yellow versus green, for example. So if we look at one of the profiles, this is just a generic cross-section through this area of the region. This is a reasonable profile of electrical data with a with a gap here in the area of the city of Rantoul, which we couldn't fly over. But we start to see, patterns of the electrical data, and we start to map out those patterns. We can draw contacts and then start to interpret the geology based on those. This is generally close to where one of Andy Stump's cross sections were, and that really the electrical data really start to define and are defined well by those interpretations as well. So we can really fill in the gaps between any data sets and cross sections with these HTEM data. So what we're going to do is take a slice, an MRI slice through the aquifer, through this county, starting from the bottom up. So in general, this is a hot cold map on the right, where everything hot you see, red and yellow, is limestone bedrock. So we're taking a slice that's all the way down at an elevation below any of the quaternary material. So the red is limestone bedrock. The blue is all shale, Pennsylvanian shales and coals. I think this is Mississippian limestone. These are dome structures. So we're going to start here and move up through the section. And as we move up in basically 30 feet slices, we start to see that we're getting in this area, we're getting into the Mahomet Aquifer here, the lowest portions of the aquifer in the county. Then we get up more into the middle and we see the aquifer diverges. We see parts of it here and parts of it through the north central part of the county. Now we're right in the middle of the aquifer. We see definitive southern boundary here as we move up through the Bedrock Valley, northern extension of the aquifer as well. It has two limbs of it, basically. We get up into the upper parts of the aquifer where we know it's somewhat cemented sometimes, and we see possibly indication of that being the darker red. And then we get up very much to the top of the aquifer, and we start to see these channels, which are amazing. We've never seen these before. We knew there were some channelization, but now we're able to image it. So we start to see channels developing in little bedrock valleys, channelization of sand and gravel deposits up north of the town of Mahomet. We really start to see these beautiful channels. And again, these are up above the bedrock, but they seem to be potentially in communication hydraulically with the aquifer. So that's one of the things we really want to try to understand, is the hydraulic communication of some of these channels. For example, this one, is it hydraulically connected to the aquifer? And as we get up further into some of the youngest glacial sediments, we get more into the greens and the yellows and the blues that are the clay cap of this confined system. So this all this clay and the blues are the moraines and the ground moraine and the glacial tills that are capping the confined Mahomet Aquifer. And we finally get up to elevations where some of these slices are above land surface. But it's a beautiful way to, let's go through that again. A little quicker. So we can start at the bottom, we come up, we see the Mahomet. It's a beautiful MRI of the subsurface. It's blowing our minds. Amazing data sets. One little case study that we looked into, we were trying to use some old data to try to confirm and verify the HTEM data. East of Champaign-Urbana, there are little towns, Sydney, Homer, Ogden. These are little towns that are either purchasing water from Champaign-Urbana or from the same water company, or they're on their own water supply. Well, this little town of Homer was looking for their own water supply. And we, in the 90s, went out with ground-based geophysics, and we were trying to find we knew there were some indications of channelization and some sand or gravel channels. And we found, after 3 weeks of field work and months of report writing and processing, we found a nice little sand and gravel channel for them to install a couple wells. And they put in a couple wells that get them about 1 million gallons a year. And after all that effort in the 90s, we come through and we fly our HTEM, and we can see with our HTEM exactly where that channel goes. This is, again, blowing our minds. Let's watch that again. So this is from the 90s. now we know exactly where that channel is. We've picked up the channel that we've picked up in the 90s, but now we see all the distribution of all these potential sand and gravel lenses that are in the subsurface. And so, like, to me, it makes us see it seem like the ground has become transparent. This is a road, Windsor Road, we all know locally. So now you know if you're driving down Windsor Road, you're driving right next to one of these sand and gravel channels. And we know now that this channel takes a nice little bend to the right if we want to explore more of it. So it's a fantastic resource. This took us 3 weeks to acquire. This area with HTEM probably took about 3 days at most. So a nice little case study that kind of shows the implications of the power of this HTEM work. Why is it a game changer? It changes the way we even perceive the subsurface, in my opinion. It changes the way we perceive aquifers. It's really going to help us understand 3D relationships between the aquifer itself and other deposits above it, and really help us define and redefine where we see and how we perceive the aquifer in itself. And if we can really bring these together and pull these into our groundwater flow models and help improve our colleagues and their predictive modeling, we can really make and transform the way we manage water supplies generally. Speaking of the cost efficiency of this is a back of the envelope kind of calculation that I've been doing. The airborne mapping for Champaign County costs us about $500,000 to acquire it at this resolution. And then total costs with staffing and drilling and all that to ground truth, it's about $1 million to $1.5 million. And we'll finish this project up in about 2 years. The acquisition cost it cost us 7 days. It took 7 days to acquire all this from a helicopter. If we were to do the same thing with traditional TEM mapping, traditional electrical mapping at the same resolution of this, it would cost us about $3.5 million just for acquisition, probably total cost of $7 to $10 million with all the rest of it. And it'll take us 12 years with absolutely no days off, no vacation days. So of course, the cost efficiency of airborne is always going to be better, but I just try to emphasize that the costs up front really pay off in the end. So up next, we've gotten funding and have started to and have actually flown a northeast portion of the Mahomet Aquifer. We just collected those data in January of this year, so we are in the middle of processing those data and start to then build this model in with what we've already discovered in the Champaign area. And then our goal is to then eventually move across the Mahomet, gain funding and support in the long run, and finish this thing off. So with that, I'm happy to take questions through the chat or however Aaron wants to make that happen. And I thank you very much for the opportunity and your attention.
Jason, thank you for the talk today. I found it really quite informative.
Awesome.
Very quickly, let everybody know that the quiz for New York should be dropped in the chat momentarily, so watch for that. I'm going to start us out with one quick question, and then we'll kind of dig into the chat and see what other questions are out there. Jason, do you guys contract this out? Do you fly this yourself? How do you actually go about getting in the air and getting this done?
Yeah, it's a good question. There are a couple of companies that we've worked with in North America, but we contract it out for sure. We have the geophysicists that are the experts for processing data, but there are a couple of companies. You can see this little sticker on the nose of this antenna is SkyTem. That's one of the companies that flies a lot of work in North America, and that's the company that we use, and they're based out of Canada. Fantastic company to work for and work with.
See a question from Mark Howell. Mark asks if the final data sets, grid files and CSV files, etc., will those be available to the public?
Ultimately, yes, we're developing different ways to distribute the data and distribute the interpretations. But yeah, it'll ultimately be all public data for sure. It's a county funded and federally funded programs. So that's one of the things we have to do is make it available.
From Rich Baldwin, Rich asks if you went deeper at Homer, were there more aquifer material?
From what we know about the geology in that area, no. So there are more aquifer materials, but they're in the deeper bedrock. So that we'd get into a limestone, fractured limestone aquifer. And if we go deeper on the order of, I'm not sure how much, but thousands of feet, maybe 1,000 feet or so, we'd get into a very regional sandstone aquifer. But at that point, we don't know if it gets a little brackish. The water quality may get a little brackish down there.
From Hugh Downer, Hugh asks, have you translated the costs into a cost per acre rather than a cost per project?
What we've gotten to so far is just cost per 1,000 square miles. So that's about $1 million per 1,000 square miles.
So
Per acre.
$1,000 a square mile.
Oh, well, yeah, there you go. There you go. Yeah,
Yeah, that's not bad.
it's not bad. You would never want to do this likely. I mean, it all depends on what it's worth, but it costs about $30,000 in mobilization. So it's going to cost you a minimum of 30,000 if you're going to do a farm field or something like that. So, and then the flight miles over the farm field, flight miles are usually around $100 per, I guess, $100 per linear kilometer. So a farm field or an acre may not be worth one project for sure.
Chuck Drake asks, how does the pilot keep the transmitter loop level, or is there an inclinometer to make adjustments?
Yeah, so there is an inclinometer on the instrument along with a altimeter, and that pilot is tracking those at all times. So he or she need to have that antenna as level as possible, and so they adjust velocity and adjust everything to keep that thing as level as possible, and they're tracking it at all times. And when then we get those data back as well, when we're processing the electrical information, we know if they were tilted a lot or not tilted, so that if an error shows up in the data, we can try to assess what the error is coming from.
From Carlos Prieto, what is the typical flying height above ground?
Oh gosh, that's a good question. I cannot remember. It's probably on the order of oh shoot, 90 meters or so. It's not too high.
Okay.
But
This from, let me see if I can get a name here. Well, from Terry Gulliver. How do you discriminate the depth of data sources?
from the electrical data, so this is I mean, I don't know how the geophysics works on it, but it's time domain electromagnetics. So that's the TEM part of it, time domain electromagnetics. So from the geophysics point of view, it's all based on time. And so time of release of the energy and time of reception of the feedback energy, so they can back calculate depths from that. That's my best explanation of the geophysics of it.
All right, from Wade Piggott, were any differences in water quality recognizable, TDS, whatever it might have been?
You know, we've been thinking about that for a long time, and we haven't really looked into comparing that yet. But that's one thing we want to do, is see if we can pick up some brackish stuff. One of the emphasis for the project also was to flying over legacy landfills to see if we can see water quality issues associated with an old landfill that may be leaching. And that may have to be a more rigorous effort. We didn't focus our flights over landfills or anything. So if we would have caught one, we may have some data. But flying every 2,000 feet, every 650 meters, may or may not catch a landfill water quality issue. But yes, certainly we want to start looking into legacy regional water quality issues and see if we can find indicators.
Another question from Chuck Drake. How do you correlate the EM signature with lithologic samples or descriptions from test holes and existing wells?
Yeah, that's been a big question. So we try different ways to do that. We have our own lithologic descriptions where we core continuously to bedrock. Like I mentioned, we probably have 100 or so of those. But we also have a lot of downhole geophysics and downhole geophysical logs, including EM. So we've taken open hole EM logs, maybe a dozen at the most, but open hole logging in quaternary sediments is so scary because you're risking collapse in the hole. But we've done it, and we have electrical measurements of all these materials, at least in one dimensions locally. So we're associating those data with the airborne data, and they're coming out quite similar. We do have some non-uniqueness problems between, for example, very carbonate-rich tills, which are clay-rich, but they're carbonate-rich, and sand and gravels. Both may have very similar electrical signals, and that's not only in the airborne, but also in our downhole logging. So with those, we try to use other stratigraphic controls on making picks in the airborne data. But long story short, we have lithologic descriptions and samples along with downhole geophysics to try to make those correlations with the airborne data.
I think that also answers a question from Ian Gottschalk, who'd asked about something very similar. So I'm going to hop down to Terry Swore. Terry asks if you've been able to detect any karst structures in terms of maybe understanding challenges for future building sites or building structures.
Yeah, and in this part of Illinois, we don't really have karsts. We don't really have karsts, at least topographical expressions. Some of the limestones up in the northeast part of the county, don't know if there are subsurface expressions of karst. Haven't really looked for it and haven't really seen it at this point.
Miguel Valencia asks, what software are you using for the data processing and geological modeling?
We have a few different data sets or data softwares. There's one called Workbench, which is the geophysical data processing software. That's what our geophysicists use. And then we are using a couple different softwares, one called Geoscene 3D, which is built also to incorporate AEM data. And from those, we can visualize them in 3D and make geologic picks and do some automated self-learning modeling of the geology, some geostatistical modeling. It's a fantastic software. Those are the two main softwares, one for processing, one for interpretation, Geoscene 3D and Workbench. And then we use another software called GeoVisionary, which is largely just a visualization software, which is very powerful.
This question from Mario Carnaval, he asks, can you discuss how well ground truth surveys support the HTEM data?
Yeah, we've had ground truthing takes so long to do. Last summer, we had a crew of students. We were able to get about 4 or 5 miles of ground-based ERT. And it came out, of course, the ground-based ERT is a higher resolution. We don't get as deep. But I have a slide of that. These are some extra slides. I'm sorry, I'm flying. Oh, here we go. Yeah. Aaron, can you see my screen?
Yeah, we can.
Yeah, okay. This is one of the profiles we've done in one part of the county. And then we went through and did a ground-based survey along that profile. And so these color ramps, I don't believe are exactly the same, but we see pretty good resolution of and comparison between ground-based and airborne. So the airborne, this is one of our first models of the airborne where we did one iteration of the inversions. We've gotten different inversions, and so what we want to do is use some of these ground-based surveys to then calibrate and recalibrate our airborne data. But so far, it looks really good.
And I just see a comment here from Jared Abraham. Jared says 100-foot sensor height, 200 feet helicopter height. So I think he's getting back at that altitude question from
Yes.
earlier.
Oh, nice. Thank you very much.
And then Harvey Thorlifson is asking if you could talk a little bit about community relations efforts and maybe some examples to show how the public perceived that survey. You know, what was their response to somebody flying a helicopter around?
Yeah, great. Good to hear from you, Harvey, longtime colleague and friend. Yeah, so we've done a lot of public outreach for this. Before a helicopter ever goes up in the air, we do community outreach. We'll have a media event, especially on the day of when the helicopter and the equipment all gets into town. We will have an open media day where we invite media, we invite local leaders, we invite public to come and see the instrumentation and actually do a demo of the flight, because, and certainly that doesn't get all of it, but we've had many calls of people wondering what in the world is happening, whether it's curiosity or they're getting frustrated or whatever it is. But we try to do our best with community engagement before the project happens, for sure. And now after the project's over, we're holding workshops, or not after the flights are over, we're holding workshops, for example, for our supporters, our local leaders, and the public to try to update them on progress. And so we have websites, and these workshops are probably going to be maybe 2 of them a year at most, but at least efforts to try to share data and share information, for sure.
Rich Baldwin asks if larger electrical lines, be they above ground or buried, impact the quality of the HTEM data.
They always do. Yep. So the larger electrical lines, we do see on the altimeter that we can track where those electrical lines are, because the altimeter goes up. So they got to fly up and over those. And wherever we have the larger lines, we have to, the data is pretty bad. So we have to eliminate those data. And it's not too much. It's maybe on the order of, 100 meters or so of transect data that we have to eliminate, because it's just all noise. The smaller electrical lines oftentimes create a little bit of noise, but usually we can work around those in interpreting the data. We can kind of pick those out. But certainly in town, we cannot fly. There's just so much electrical data everywhere.
All right, 2 more questions here. One from
Sure.
Odimikan Idowu. Odimikan, I apologize if I mispronounced your name. They ask if it's possible to use data collected to determine aquifer potential and estimate drawdown.
Yeah, that's the one thing we want to look into as well, is can this thing pick up in an unconfined system? Can it pick up water table or pick up any indication of drawdown around wells? We've explored that a little bit with ground-based and to mild success. But again, with the airborne, we haven't looked into it as much. We haven't honed in on, for example, the Champaign-Urbana cone depression. So there is a constant equilibrium cone depression in Champaign-Urbana. We need to really look at the data and see if we can see any indication of that. It's a confined aquifer, so my guess is likely not. But yes, one thing that people are trying to do is to understand flow systems, the actual water flow systems.
And our last question from Carlos Prieto. Did you have overlapping data, or did you have to interpolate between flight lines?
we most flight lines, we kept them closely enough spaced to where we felt like the resolution could correlate, at least in that sense, a regional sense. We do have tie lines, though. We had about 2 or 3 cross-county tie lines that were diagonal that went across all 79. So point is, we had a couple tie lines that crossed everything, and those we use as a calibrative tool. But most flight lines were not crisscrossing.
Great. All right, Jason, thank you very much. I really appreciate you sharing your time and expertise with us. Just a quick reminder to our attendees, the quiz for New York CEUs was dropped in the chat at about the 11:51 a.m. mark. Wendy may drop it one more time, so keep your eyes open for that. You will have an hour to complete it, and you do need to get 4 of the 5 questions correct. You may take that as many times as you like, so there's no limit to the number of times that you can take answer those 5 questions. Jason, thank you again. I really appreciate it. And to the rest of you, next month we will have our Lunch and Earn seminar scheduled for the last Tuesday of May. I think we may have Rick Coles come back and speak in a little more detail about his project, since he had really more information than we had time. So keep your eyes open for that. If any of you are interested in presenting a webinar yourself, please reach out to me directly. My email's on our website. Be happy to talk with you about how that works and try to get this all scheduled and moving forward. Thank you very much, everyone.